All right, so now we're going to talk about affine connections, which, if you recall, is a way of generalizing the notion of a directional derivative to a manifold. So affine connections. All right, so we want to generalize the notion of a directional derivative to a manifold. And this involves introducing the notion of an affine connection Okay, so let's try to do this in a somewhat abstract way to begin with. Okay, so let's say we have this. It's like denote the set of smooth vector fields. On M, okay, then an affine connection let's write this in the following way. So this is del or nabla. Okay, on a manifold M. Okay, is a mapping from two copies of the space of vector fields to the space of vector fields. Okay, so nabla is a map from two copies of the space of vector fields to the space of vector fields. So more or less, it's like given two vector fields, it gives you another one. Okay, which is denoted by so eta cos C maps by nabla right to nabla eta cos C. Okay, and it satisfies the following. Okay, so the first one is what's called FM linearity. Okay, so FM is just the space of scale-valued functions. It's like on M. Okay, so in the first slot, right, if you take essentially linear combinations of the vector fields, sort of pointwise, right? So I have F times nabla plus G times, it's like chi, okay, times C, right? This is going to be F okay, so so again, it's like perhaps the easiest way to think about this is in a pointwise sense, right? This is sort of the notion of linearity. It's like pointwise, but what happens now is you're allowed, it's like to have flexibility to multiply the vector field by a different scalar function value. It's like at different points in the manifold. Okay, So this is the set of scalar functions on M here. Okay, the second one is R linearity. In the second slot, let's see, in eta, C. So that means that if I do this, right, I have AF plus B, sorry. Okay, so if I take now a linear combination, it's like a two vector fields, right? But now A and B are constants, right? So here F and G were scalar valued functions. So A and B have to be constants here, right? So this is that combination. So in both cases, you can treat this as it being defined. It's like at the level of sort of the in this pointwise sense. But the main issue is that whereas in the first slot, you're allowed to have essentially the weights change from point to point of the manifold. In the second one, it's like those weights have to be constant over the entire manifold. Okay, and then the third one is a product or Leibniz rule. Okay, and and this has to do with the fact that this is going to be something like a directional derivative, and so the directional derivative satisfies the Leibniz rule. So you want this to satisfy the Leibniz rule as well. Okay, so Leibniz rule applies to when you take f multiplied some scalar multiplied by this vector valued function, right? Then that's equal to the following. Okay, all right, so these are these three properties which involve introducing this notion of an affine connection. All right, and then once you have this affine connection, then this object here becomes what is called the covariant derivative, right? So the vector field nabla sort of eta c, right, is the covariant derivative of c with respect to eta, right, for the affine connection nabla. Okay, all right. So let's see how this sort of comports with the usual notion of a directional derivative. It's like in Rn. So in Rn, right, the classical directional derivative defines an affine connection. Okay, so let me write it this way, right? So if you have nabla, it's like eta cos c at a point x, right? This is just going to be, again, if we're in Rn, the usual limit as t goes to 0 of this vector field, okay, evaluated at a point x plus t eta. okay, minus cos c at x divided by t. Okay, so and so what I mean by cos c sub x is that I'm evaluating the vector field cos c at the point x, right? So if you're paying attention, it's like then you'll realize that when I take x plus t times eta, right, I have to use this canonical identification which we have in vector spaces between the tangent space to the vector space and the space itself, right? So again, in vector spaces, we tend to sort of, blur the distinction. It's like between a point on the manifold or the point in Rn, it's like, and the tangent vector to Rn, and we identify it in sort of a canonical way. Okay, so where we use the canonical identification Txe with E, right, in order to make sense of x plus t times eta. Okay. All right. So anyway, so in particular, it's like the sort of the usual directional derivative, it's like which we have, right, in Rn is indeed an affine connection. So that at least is suggestive that we're on the right track, right? That this is potentially a generalization of the notion of directional derivatives. It's like on Rn. Okay, so and we'll see that there are other properties. It's like which reinforce it's like this this property. Okay, so let's look at the following proposition. And the proposition basically says that if you have a sort of every manifold, where here it's like I'm assuming that a manifold is one which is second countable in Hausdorff, right, which is sort of the classical notion of manifold. Every manifold emits an affine connection. Okay, so we state a proposition. Every second countable Hausdorff manifold admits an affine connection. Okay. So let me try to prove this. Oh, actually, let me not try to prove this. Let me sort of just remark about that. Okay. All right. So in fact, every manifold has infinitely many affine connections. Okay. Not all of which are easy to compute with. It's like some are easier to work with than others. So let's sort of characterize all possible affine connections on a linear manifold. Rn. Okay. So what we're basically going to try to do is that we're going to try to distill, it's like the essential things you need to prescribe in order to, to have, it's like an affine connection on Rn. Okay. And the way to sort of think about this is that when we talked about, well, we introduced the notion of an affine connection, we had these properties. It's like we want the affine connection, which is a map from two copies of the space of vector fields to the vector fields, right, to have. And then what we're going to basically do is that we're going to see what those properties, it's like how those properties constrain, it's like what you can do with the affine connections. Okay, all right. So, and of course, it's like one critical observation is that it's like there are these various notions of linearity. It's like essentially there's a bilinearity. It's like for this map, so it's natural to work in a basis, right, for Rn, and then see how this sort of affine connection acts on basis vectors. Okay, and the basic idea, as is oftentimes the case, it's like when you're trying to characterize linear transformations, is that all you really need to do is to look at how it's like, again, how a particular linear or multilinear map acts on the basis vectors, and then once you have that, that's all you really need. And the rest of the action, it's like on the rest of the vector space, is obtained by linear extension. Okay, so that's basically how we're going to proceed here. All right. Okay. Okay. So let sort of E1 to En, right, be the canonical basis. Rn. Okay, so if nabla is a connection on Rn, then what we have is that, so I'm going to write down this generally. Okay, so nabla eta c, all right, and then I'm going to write it's like eta and c in terms of a linear combination of basis vectors, right? So this is equal to, all right. So this is nabla. Okay, then there's a sum for eta I, ei. Okay. Oftentimes it's like, okay, so oftentimes you'll see these supers and subscripts. It's like, and there's what is known as the Einstein summation convention, where if you have a raised index and a lowered index like this, and they have the same dummy variable, then there's an implicit sum, it's like, which shows up. So oftentimes in the literature, instead of having the sum, you just have eta superscript I, e sub I, and there's an understanding that I'm summing over the i's here. Okay, but right now I'm just going to do this sort of explicitly. There's a sum over I here, and then there's a sum over j of Cj, Ej here. Okay, so so now it's like by there's Fm linearity, right? So by Fm linearity in the first variable, okay, I can take this sum out, right? This is sum over I. And then again, it's like I can use by R linearity in C, right? This is equal to sum over I and j actually, no, I don't want to use that. Sorry. I want to use it's like the Leibniz rule, right? By the Leibniz rule. Okay, and the reason why I have to use the Leibniz rule is because, you know, it's like, because C is a vector field, right? So it doesn't, these coefficients, because C super J, vary as a function of position, right? So these are functions, if you will, multiplied into these vectors. And so if you used, you can't use, yeah, you can't use, it's like R multilinearity, it's like to pull this out, if you will, the sum, okay? But you can use the Leibniz rule here, okay? So that's what I'm going to do. Well, technically speaking, it's like what you're doing is that you're using the Leibniz rule and our multilinearity, okay? Our linearity. Okay. So, because there is a constant, if you will, right? So you're writing this individually as these sums. It's like in each of those terms, it's like in order to pull the f out, you have to use the Leibniz rule. But you also need to use the R linearity because it's not just one of these f times vector field things. You have many of them. So you have to use the R linearity part as well. Okay, so anyhow, so you have this. Okay. Okay. So I should say that the Leibniz rule is sort of applied with the terms switched, right? So this comes from the following version of the Leibniz rule. I mean, it's like it's the same Leibniz rule, but the terms are sort of ordered in a different way, right? Right. So sorry. So in particular, this term here, right, has to do with yeah, it has to do with this kind of vector field, right? So NF acting on this, right, is like a derivative, right? So this is the derivative operator associated with that. Okay. All right. Well, maybe let me just write it in this way. So what I'm actually doing is that I'm applying the Leibniz rule in this way, right? Right, that's basically what I'm doing. Okay, right. So this term here, it's like becomes this term here, right? Then this term here, right, becomes this term here. Okay, and then yeah, and then there's the eta I, it's like which was outside all of that, right? Okay. Yeah. And so we had this, and then it's like we summed it over J. It's like, and then the summing over J is where you use the R linearity in the second slope. Okay. Alrighty. So, right. So we have the bottom line, if you will, right, is that you have a term which looks like the usual thing. It's like what you're familiar with. In terms of the directional derivative, and then we have this additional term. It's like which we are not quite as familiar with, and you know that when you apply the affine connection, it's like with these pair of vectors, it's like you again get another vector. Okay, so you can then write that's like the output of this as a in the basis again, okay? And what you have then is that, what you have then is that the action of this affine connection is in some sense uniquely determined as like by this entry here, right? So the action, or sort of the affine connection, is uniquely determined below EI, EJ, okay? And I want to write this, it's like in a basis, in actually the same basis, E1 to En, okay? And what I do is I write this as, so being a bit sloppy here, this should be a subscript, okay? So this is going to be some coefficient, right? Ij, and then there's a k, and there's an ek here. Okay, so what I'm saying here is that I write down, it's like the output, it's like of the affine connection, it's like applied to ei and ej, right? And this is another vector, it's like which I again expand, it's like in this basis, and the coefficients, it's like to that are these, it's like gamma ijk terms. Okay, so these are what are called the Christoffel symbols. So in particular you have this, right? So the gamma ijk, right, called the Christoffel symbols. And then, so there are n cubed of those, right? So there are n cubed entries. And these are just smooth functions, which are each smooth functions on our n. Okay, and then each choice sort of defines a different affine connection. On our n. Okay, so in particular, as we said before, it's like this entry here is what you would typically associate with the usual notion of a directional derivative, right? The classical directional derivative, it's like on Rn. So you might expect then that if you wanted to recover the classical directional derivative, it's like then these Christoffel symbols should vanish, right? So the Euclidean connection right, corresponds to the Christoffel symbols being identically 0. So as you might imagine, then you want to be able to generalize this. It's like to a manifold. Okay, so let me just stop here for a minute. It's like, and then we'll talk about how to generalize this to manifolds. All right.